Take a good look at the night sky. All of it, the stars, the galaxies, the shimmering nebulae, everything our most powerful telescopes have ever seen is just a tiny fraction of what's actually out there. All that visible stuff makes up only 5% of the universe. The other 95% is a cosmic ghost composed of two mysterious substances, dark energy and dark matter. Dark energy is the strange force pushing everything apart, making the universe expand faster and faster. But dark matter? That's the bigger mystery. It makes up about 27% of the entire universe, which means that of all the times matter times the stuff that has gravity, a staggering 85% is completely invisible. It doesn't emit, absorb, or reflect any light. Our eyes can't see it, and our instruments can't detect it. And yet, its gravity is the only thing holding our galaxy together. Without dark matter, every star in the sky, including our own sun, would be flung out into the cold, empty void. We are swimming in an ocean of this invisible material, and scientists are in a desperate race to find it. The story of how they even realized it was missing is a cosmic detective story, one that begins with a famously grumpy astronomer who refused to believe the universe played by the rules. Section 1. The initial anomaly, Zwickie's Danko Materie. Our story kicks off nearly a century ago, back in 1933, while the world was in chaos. A brilliant and notoriously prickly Swiss astronomer named Fritz Zwicky was staring at the sky from a quiet observatory in California. Zwicky was studying the Coma cluster, a gigantic swarm of over 1,000 galaxies, some 320 million light years away. He was measuring how they moved, expecting to see them orbiting the cluster's center in an orderly way, held in place by their combined gravity, like planets orbiting the Sunday. But what he found made no sense at all. The galaxies were moving at insane speeds, way too fast for the cluster to hold on to them. Based on all the visible matter, he could see all the stars and gas in those thousands of galaxies. There just wasn't enough gravitational glue. The entire cluster should have been flying apart, its galaxies scattering like dust in the wind. Zwicky did the math. To account for the speeds he was seeing, the cluster had to have hundreds of times more mass than what was visible. And Zwicky was a man who trusted his data, no matter how wild the implications. He proposed a radical idea. The cluster must be filled with some kind of invisible, non-luminous matter. He called it Danko Materie, German for dark matter. It was an extraordinary claim. He was saying that most of the mass in this colossal structure was completely invisible. For decades, nobody really listened. The idea was too strange. Zuki's abrasive personality didn't win him any friends, and his discovery was brushed off as a weird anomaly. The universe, everyone assumed, was made of the things we could see. It would take another 40 years, and the work of a persistent, meticulous astronomer who had to fight just to get time on a telescope to prove that Zwicky had been right all along. Section 2. The breakthrough hero, Vera Rubin and the spinning galaxies. Enter Vera Rubin. In the 1960 seconds and 70 seconds, astronomy was not a friendly place for women. Rubin had faced roadblocks her whole career. She was Vassar College's only astronomy graduate in 1948 and was famously rejected by Princeton's graduate program because they didn't accept women. But Rubin wouldn't be stopped. She earned her PhD at Georgetown, where she wasn't even allowed in her own supervisor's office. By the late 60 seconds, Rubin was at the Carnegie Institution in Washington, D.C., where she partnered with instrument maker Ken Ford. Ford had built an incredibly sensitive spectrograph, a tool that could measure starlight with stunning precision. Together, they set out to answer a simple question: how do spiral galaxies spin? Now, Physics 101 says a galaxy should spin like our solar system. Most of the stuff you can see is packed into the bright center. So, just like Mercury orbits the Sun much faster than Neptune does, stars on the edge of a galaxy should be moving much slower than the stars near the core. If you plotted their speed on a graph, the line should shoot up and then drop off. In 1968, Rubin and Ford aimed their telescope at Andromeda, our closest spiral neighbor. Night after night, they carefully measured the speeds of stars and gas clouds. When they plotted the data, the result was jaw-dropping. The graph wasn't what they expected at all. It didn't fall off. Instead, it was times flat asterisk. Stars at the very edge of Andromeda were moving just as fast as stars near the middle. This was absurd. It was like finding out Pluto zips around the Sun at the same speed as Mercury. The galaxy's visible matter didn't have nearly enough gravity to hold onto those speeding outer stars. They should have been launched into deep space, like kids thrown from a merry-go-round spinning out of control. At first, they thought it might be a fluke, something weird about Andromeda, so they looked at other galaxies. And then more, they studied the 60 spiral galaxies, then over 200. Every single one showed the same bizarre behavior. Every galaxy they measured was spinning too fast to hold itself together. The evidence was overwhelming. Just like Zwicky found with galaxy clusters, individual galaxies were also missing a huge amount of mass. Rubin concluded that every galaxy must be wrapped in a massive, invisible halo of dark matter that stretched far beyond its starry edges. This halo contained most of the galaxy's mass, and its gravity was what kept the outer stars in line. Though some were skeptical at first, Rubin's meticulous work convinced the scientific community where Zwicky had failed. She had found the first persuasive, direct evidence for dark matter. It wasn't just a quirk, it was a fundamental feature of the cosmos. The missing matter problem was real, and Vera Rubin had just shown the world that 85% of the universe had been hiding in plain sight. Section 3. The Pile Up of Evidence. Vera Rubin's discovery opened the floodgates. Once astronomers knew what to look for, they started finding evidence for dark matter everywhere. It wasn't just one thing, but a whole pile of clues from different corners of cosmology, all pointing to the same unavoidable conclusion. The ghost was real. One of the most powerful lines of evidence comes from something Einstein predicted: gravitational lensing. Massive objects literally warp space and time, forcing light to bend around them. This means a huge object, like a galaxy cluster, can act as a cosmic magnifying glass, distorting the light from things behind it. By measuring how much that light is bent, astronomers can weigh the object doing the lensing. And time again, they found the mass needed to create the lensing was far greater than the mass of all the visible stars and gas. The most spectacular example is the Bullet Cluster, a cosmic crime scene located 3.7 billion light years away. It's actually two galaxy clusters that smashed into each other in one of the most violent events since the Big Bang. With X-ray telescopes, astronomers can see the normal matter hot gas in glowing pink clumps. As the clusters collided, this gas crashed and slowed down, getting left behind. But the gravitational lensing map shows that most of the times, mass asterisks colored in blue passed right through the collision without even slowing down. The dark matter sailed through the crash untouched, leaving the normal matter in its dust. It was stunning, direct proof that dark matter is real and that it barely interacts with anything except through gravity. The second crucial clue comes from the beginning of time itself, the cosmic microwave background, or CMB. This is the faint afterglow of the Big Bang, a baby picture of the universe when it was only about 380,000 years old. Satellites have mapped this ancient light, revealing tiny temperature differences. These little hot spots were the seeds of everything we see today. Gravity pulled them into the galaxies and clusters that fill our universe. But there's a problem. If you only account for normal matter, there hasn't been enough time since the Big Bang for gravity to turn those tiny seeds into the vast cosmic web we see today. Early on, pressure from light would have smoothed out any clumps of normal matter before they could grow. Dark matter solves this. Since it doesn't interact with light, clumps of dark matter could start forming much earlier, creating deep gravity wells. When normal matter was finally free to clump together, it fell into these pre-existing dark matter scaffolds. The patterns in the CMB are a perfect match for a universe made of about 5% normal matter, 27% dark matter, and 68% dark energy, the standard model of cosmology. Finally, there's the sheer structure of the universe. When you map out millions of galaxies, you see they aren't scattered randomly. They form a vast, interconnected network of filaments and voids the cosmic web. When scientists run computer simulations of the universe's evolution, the only way to get this web-like structure is to include a massive amount of slow-moving, or cold, dark matter. The simulations show dark matter's gravity pulling normal matter into these long filaments, which then light up with galaxies. The fact that these simulations are dead ringer for the universe we actually live in is another powerful piece of the puzzle. From spinning galaxies to cosmic collisions, From the afterglow of the Big Bang to the cosmic web, every line of evidence points to the same thing. Something massive, invisible, and deeply mysterious is running the show. The question is no longer times if times it exists, but times what times it is. Section 4: The Modern Hunt. Knowing dark matter is out there is one thing, actually finding it is another story entirely. For decades, scientists have been on one of the greatest ghost hunts in history. So, how exactly do you catch a particle that's invisible and barely interacts with our world? They are trying three main strategies: make it, break it, or shake it. Making it happens at places like the Large Hadron Collider at CERN. The idea is to smash normal particles together at nearly the speed of light and hope that, in the fiery debris of the collision, a dark matter particle pops into existence and flies away. Physicists would then look for missing energy, a telltale sign that an invisible particle escaped. So far, no luck. Breaking it, or indirect detection, is about looking for the evidence of dark matter destroying itself. If dark matter particles are their own opposites, they should annihilate each other when they collide in a dense area, like the center of our galaxy. This cosmic smash-up would release a shower of other particles, like high-energy gamma rays. Recently, a tantalizing, though still unconfirmed clue emerged from the Fermi Gamma Ray Space Telescope, a strange glow of gamma rays from our galaxy's core. Scientists are still debating if it's the smoke from an annihilating dark matter particle or just a cluster of exotic spinning stars, but it's one of the hottest trails they have. The third and most direct approach is shaking it. Direct detection experiments are designed to spot the incredibly rare event of a dark matter particle bumping into an atom here on Earth. To do this, scientists have built some of the most sensitive detectors ever imagined and buried them deep underground in mines to shield them from any other particles that could create a false signal. The leading candidates they're looking for are called WIMPs and actions. WIMPs, weakly interacting. Massive particles are heavyweights, and experiments like xenon use huge vats of liquid xenon, waiting for a WIMP to knock into a xenon atom and create a tiny flash of light. Actions, on the other hand, are incredibly lightweight. Experiments like ADMX use a powerful magnet, hoping to convert a passing action into a single particle of light that they can detect. And the technology is getting even more creative. Scientists are now designing networks of quantum sensors that could feel the subtle, wave-like disturbance of a light dark matter particle as it passes through. It's a revolutionary new front in the search, leveraging quantum physics to hunt for a substance that has dodged every classical attempt to find it. The hunt is on, from the deepest mines on Earth to the most powerful colliders and telescopes ever built. This journey into the invisible universe is one of the greatest adventures in science. If you love exploring the biggest questions out there, hit subscribe and join us for our next trip into the unknown. Conclusion: we live in a cosmos dominated by a substance we can't see and don't understand. The 5% of the universe made of atoms, the stuff of stars, planets, and us is just a foam on a deep, dark cosmic ocean. All of our science, our entire understanding of physics, has been built on this tiny sliver of reality. The work of astronomers like Fritz Zwicky and Vera Rubin wasn't just about finding something that was missing, it was about revealing our own ignorance. They showed us that the universe is far stranger and more mysterious than we had ever dreamed. And the evidence that followed, from gravitational lensing to the light of the Big Bang, has cemented the dark matter as a fact of modern cosmology. Today, the quest continues. The Vera C. Rubin Observatory, named for the woman who changed our view of the cosmos, is set to begin a new survey of the sky. It will create the most detailed map of dark matter's influence ever made, carrying on the legacy of its namesake. The eventual discovery of a dark matter particle will be a turning point for humanity. It won't just be checking a box on our cosmic to-do list. It will open up a new era of physics beyond the theories that have guided us for 50 years. The fact that 85% of the matter in the universe is missing isn't a failure of science. It's a sign of its success. It's the honest admission that there is more to learn, a cosmic puzzle of the highest order waiting for a solution. And it's a profound reminder that even after centuries of staring up at the heavens, we have only just begun to see what's really out there.